My name is Nima Ashtari. I'm the CEO of Foresight Analytics and X-Matik. I've been in the automotive industry for about 10 years and doing a lot of engineering work for companies like Honda, Magna, and Tesla. And then kind of went off to the self-driving space and started doing a lot of work in trying to bring aftermarket technologies to bear. And I'm here because I think machine learning, self-driving is probably the most interesting applied machine learning problem out there. And I'm sure our panelists are going to agree it's one of the best problems to try to solve. So without further ado, I'd like to also ask them to introduce themselves. Maybe Inmar, if you could go ahead and tell us a little bit about the work you're doing.
Sure. Hi, everyone. Thanks for joining the session, and Nima for moderating, and Vlad for being my co-panelist. So I work as a director of engineering at the Research and Development Office of Uber ATG. So ATG is the self-driving division for Uber. There is a research lab that was started in Toronto about 3.5 years ago, and we go by the name of R&D. But really, our focus is primarily AI for self-driving, and in particular, deep learning for self-driving. So we do a lot of work that is very focused on how do we solve problems for which we don't believe there is a proper solution yet, that require the more scientific approach or scientific mixed with engineering, but not pure engineering. The team that I manage and lead takes a lot of the research artifacts, so the prototypes and papers that come out of from the pure research side of the lab, which, by the way, publishes everything that they discover as part of our approach for how we think this is a problem we want to involve everyone in and share our discoveries. So I've posted a link for anyone interested in looking at the publications themselves. But a publication is at the end of the day a step forward, a proof of concept, and my team deals with how do we take this technology and actually get it on the car and get it into the production system and make it robust and reliable and run fast enough so that we can, drive using these new exciting technologies. And just one thing, my background is in machine learning. I did my PhD at the University of Toronto, specializing in machine learning, and since then have worked in industry pretty much on this intersection of exciting, cool, new machine learning-based technologies and production systems.
That's really excellent. Great to have you, Inmar. Vlad, if you could give us a little bit about yourself and Helm.
Absolutely. Yeah, so my name is Vlad Voroninski. I'm the CEO of Helm.ai. And what we're focusing on at Helm is building the next generation of AI technology for autonomous driving. So our end goal is L4, fully autonomous driving, but we license our software for L2 and L3 consumer vehicles as well, and that's essentially the first product is going to be focused on that. The core differentiating factor about Helm is coming from technology that we developed internally that we call deep teaching, that allows us to train neural networks on very large data sets without requiring annotation or using very minimal annotation, which allows us to essentially achieve, max out the capacity of the neural networks to get as much accuracy as possible across a lot of different object categories. And to give you a sense of my background and sort of where some of these innovations are coming from, so I've been working for about 15 years in the field of computer vision AI. So at least when I started back at the UCLA Vision Lab, got some exposure to the DARPA grant challenges back then. But my perspective has been that the core bottlenecks for AI are rather mathematical. And so I was an applied mathematician in academia for about 10 years. So did a math PhD at Berkeley and also did a postdoc in the math department at MIT, but always had sort of a machine learning bent to my work. And I was an expert in an area called compressive sensing, which does, has informed quite a bit my views on artificial intelligence, and also has impacted our work on deep teaching. yeah, so I'm happy to be part of this panel and looking forward to the discussion.
Excellent. So one of the very kind of obvious things that everybody wants to talk about when it comes to self-driving cars is when is it ready? When is it good to go? Obviously, we've had a lot of questions that came from our committee in regards to that. But it seems to us that from a machine learning perspective, the real question is how good is good enough? And I wanted to kind of put the question out to you. How do you guys think about validation? How do you guys think about generally what is a good enough answer to the question of is this neural network doing what it intends to do, which is to drive the car or in concert with other networks drive the car? And where do you think the benchmark needs to be? And where are we with respect to that benchmark? So maybe just have Vlad comment on that first, and then we'll go back and forth a bit.
Sure. Yeah, so I think that there's kind of two separate questions. Like one is what makes for a deployable product, right? Sort of what is the criteria you're putting in place for that? And you're just looking at some sense of statistical validation for, okay, it's safer than a human by some factor, or you also have to have a certain amount of interpretability to handle various liability questions that will inevitably come up. But once you've kind of defined your product, then you can boil it down to certain sort of scientific metrics across across the stack, perception, intent prediction, planning and control. And there, I think it becomes kind of more deterministic. So there's certainly ways of essentially creating difficult validation sets, right, for the system. If you're not simply relying on scale, if you can rely on scale and simply get a statistical estimate of the quality of your system, which I think today is really only possible on various consumer fleets, right? So that's the only way you're going to get enough data to get a true statistical pure estimate. Otherwise, you can rely on certain sort of data sets that dig into the really hard parts of the task, right? So, for example, right, how do you test an automotive brake, right? You don't just necessarily drive a car around for like 100,000 miles, but you can put it under a lot of stress and stress test the system. So if you can design such tests across the entire stack, you can actually get a pretty good sense for how well it might perform.
Inmar, do you think just kind of testing individual components of the total stack is the means of getting to good enough, quote unquote, for mass deployment?
No. The way that we think about it is you have your system subcomponents, and each one of them is, each model is associated with the model level metrics, and typically these are well defined, often by some blend of academic metrics as well as ones that are more suitable for the real world. And so whenever you have a new type of model that you want to try out, you first go through your model level metrics and evaluate it, and you want to see some improvements. And then you look at the system level metrics, which really are testing the end-to-end system. And so for that, Uber has been working on defining these basically pass-fail type of scenarios where, it doesn't matter how good your particular new perception system is. If you're not passing this particular scenario, you're like, this is not going to go on the car. And the way that these scenarios are tested are, first of all, in simulation. So we might get to talk about simulation a bit more later, but simulation is really important because this is where you can test rare types of events that you still want to be able to test. So you can go and record, hundreds of miles or thousands of miles or millions of miles of really boring road in the sense that it's not really testing your stack. There isn't a lot of uncertainty. There isn't a lot of, small objects that you need to detect or situations that are complicated. So simulation really allows you to do it safely. So that's one type of testing that you do. And then once you're done with your simulation and you've passed all of these pass-fail scenarios, then you take it to the track. So we have a facility in Pittsburgh that's basically like a fake little city with a lot of different roads and traffic signs and so on. And it's a mix of self-driving vehicles as well as human-driven vehicles that are basically stressing, as Vlad said, the system And these give you, on the one hand, it's not as good as simulation because there's a limit to how much you can test. It's time consuming, it's manual, you don't want to put anyone at real risk. But on the other hand, it's fully testing the car with the sensors, with everything. So it's not a simulated setup. And in addition to that, going back to the model level metrics, we're also trying to kind of set the standard for how do you test different types of models, what are the metrics to look at. And so the lab has been for many years working on benchmarks, sort of like the QT data set, and now there is a new one that I think was just recently released at IROS, which is basically data as well as associated metrics and benchmarks so that different people working on the problem can basically evaluate their individual modules to see how well they're doing.
I mean, that's such a great point around simulation here, because it's gonna, a lot of people believe it's gonna play a pivotal role. And then some people really believe that simulations are essentially a recreation of the life that we live, the real world. And if you could manage to do such an amazing job, then you've already solved a way more difficult problem than even self-driving itself. What do you say to those who say simulations are not going to really help and they don't really ever end up representing the real world? How do you respond to those folks?
So the big problem with simulation systems, the one that are available is in my mind, and like this is also what we believe is the sensor simulation side of things, because that's where it's unclear that you were actually giving the right type of information to a neural network that at the end of the day has to work in the real world. So we spend a lot of time working on sensor simulation technology, and some of the most recent exciting stuff is about simulating LiDAR and simulating camera in a way that doesn't just look good. Because the video games are looking great, but they don't have the photo, the physical properties that might actually be important for the neural network. So we're working on basically like how do we cleverly simulate sensors, which we think is very, very important. And that allows you to fully test your stack. So from perception to prediction to motion planning to, as opposed to a lot of systems that either assume perfect perception. So you're like assuming that you got all of the pedestrians and cyclists and motorcyclists and so on, which is not realistic, I agree. And then only testing the motion planning component, or systems that are based on actual data captured outside. So you can go and record stuff and then rerun it. So this is typically referred to as log-based simulation or something along these lines. But then if the car decides based on an update that you are now testing to turn right, the log is not going to change because the car still drove straight in the original thing. So these two approaches, like only testing the control system, also prediction and control, and only testing the perception system, we're really working on like this integrated system that will allow us to fully test. And we do believe that this will make a difference. And again, going back to this really hard to capture in terms of data situations where something really dangerous is happening, and you want to know how is the car going to react in this situation when you don't have any other safe, reliable way of getting some sort of signal about it.
Vlad, do you have any take on that? And while you go on that, Inmar, if I could have you do a little muting. It is a little bit hard with the background noise while Vlad's speaking, then we'll see if you can find maybe a headphone or something. Yeah, go ahead.
Yeah, sure. So yeah, I think simulation can play a role, right? I think that at the level, for example, of creating some kind of a physics engine representation of the world, right? And let's say that you actually had good enough intention models for all the different agents, then you could use that to probably just even use like reinforcement learning to train an optimal policy, right? So at that level, I think simulations can be quite useful. At the level of simulating sort of for perception or for intent, right? I think there would be rather challenging. And I think that for perception to assuming that you're trying to do the simulation in the form where you actually get data that's can be used for validation purposes, right, in a scalable way, I would say that simulating perception is probably roughly as hard as solving the computer vision problem, let's say, right? If you're talking about images. And so I don't think that it's really, there's just a question of, okay, well, if you want to take the simulation route as your solution to computer vision, then great. But otherwise, it's not like it's some simulation is some trick you can play to kind of necessarily make things a lot easier at that level. So yeah, I mean, I think as Inmar mentioned, like things like simulations for things like computer games, etc. I mean, they're essentially very idealized versions of the world, and to us, they can be like just as interpretable as real data, but can still have it can be quite a lot of dimensionality of the data that actually doesn't look like anything like data from the real world. And for training neural nets, that really might not be good enough. So you have to do a lot better. So yeah, I kind of look at simulation as not necessarily doing anything special at the perception layer.
Well,
can you hear me now? Is this better?
Much better. Thank you so much.
Yeah.
Perfect.
I also have something like just about we agree that roughly speaking, this is a hard to solve computer problem, computer vision to actually simulate it. So the approach we're taking, and there are a couple of papers you can read about it, is not to try and generate the assets, but actually to take real world captures and build assets from them. So that's the whole different way in which we're looking at it. So for example, you can build, the typical way simulations are generated is some artist builds a model of a car, like a CAD model of the car, and then you do something called ray casting, which you're basically saying, okay, the physics of it is like a bunch of light rays are going to go and reflect, and we're going to calculate it. What we're saying is different. We're going to go out there, we're going to capture, say, a LiDAR point cloud, which is real data, and from that we build the asset. And so, but that you can actually now put in a different type of scenario that again is built from real life captures of data. So it's about manipulating this data rather than generating the data.
Sure, no, that's reasonable, right? I mean, yeah, if you're blending with real data, then it's more promising.
What about simulations for the control side of the problem, though? It seems that the similar problem could be presented in that behaviors of agents is quite complex once you actually try to calculate intent or try to understand intent in order to know kind of what they're going to do. And so it's not something that you could kind of maybe at a car that's going at 100 kilometers an hour has so much momentum that you can only go a certain way, just physics wise, but a person or a pedestrian who's walking and can very instantly change direction. How do you see simulation playing a role in the dynamics elements, or at least the motion planning elements of the neural networks that you're training?
Yeah, so that's all part of our grand vision for kind of this new generation of simulators. So great question, because it really leads to something that we're thinking about. So we're also building models of intelligent actors, which are beyond being realistic from the perception side of things. They also, and again, the idea is always, can we learn from examples? Can we learn from the real world? And by that, the power of not having to handcraft it, but rather learn behaviors and learn reactions, can we introduce and inject into the scene actors? And one of the interesting aspects of that is, for example, that we're building the technology for is this idea that these different actors are reactive. They're seeing each other, all of them are seeing all of them and reacting to each other, right? And so you need to also take that into account.
Vlad, any more comments on that? Just because I do want to touch on a couple other concepts.
Sure. Yeah. I mean, on intent prediction, I'll just give kind of my high-level view, right? I mean, our approach to that would essentially be to first, really attack the perception problem, and then take kind of a large data approach to intent prediction, right? So if you can featureize all the agents in your different scenarios that you're looking at a very fine level, and actually have very robust, perception, you can basically map everything down to a lower dimensional state space, and then it becomes kind of a more tractable problem that you can really try to solve at scale, right? And not just in terms of, it's also about how these agents interact with the rest of the world, right? So you'd have to kind of parse the entire scene very accurately. But yeah, I mean, essentially we believe that would put us in a good regime for learning intent models at scale and not having to like feature engineer too many things. So yeah, I guess I roughly think about intent prediction as a kind of a perception complete problem.
Excellent. So something that a lot of folks like to think about when it comes to self-driving cars is the corner case, right? Specifically, even in the perception case, where you're talking about an object that you just couldn't foresee, or an orientation or a situation of an object, or a particular occlusion of it that you couldn't foresee, you know, and a lot of companies doing classes for all these different types of things you might encounter. Did you forget the class for raccoons? Did you forget the class for bent over garbage cans, and so on and so forth? And does this problem ever end? So I just want to take kind of what you guys think is the ultimate answer to that problem down the line with enough engineering, and then also kind of try to bound that answer with, okay, what is the engineering effort required to actually achieve that? Is it something in the order of landing a Mars rover, or is it something in the order of making Facebook? You know, just kind of give us a sense of how big an engineering challenge is this?
So I can go ahead. It's obviously not reasonable to try and classify every object in the scene, because there are way too many things that we need to worry about. So the approach we're thinking about and you know, researching, and again, there is some stuff out there for people who are interested in reading more, is this idea of things and stuff. So there is like, you know, some things we do want to accurately say, okay, we think this is a pedestrian, we think this is a cyclist, but you know, a cyclist holding a dog and, you know, a bucket or whatever of flowers, that might confuse that type of system. But you want to know that there is a coherent set of pixels or points in your point cloud that are that seem to be behaving as a thing, and therefore you at the very least avoid, you know, coming close to it and colliding with it. And that is a reasonably scalable approach, because you don't need to map out the entire world of everything possible. You can also talk about building, and again, you want to recognize and detect the important things that you know and you want to know how to deal with, and you always want to leave some amount of possibility of the things that you're not sure about, and to have reasonable behavior around them. So these are like various types of fail-safe mechanisms that you can introduce into your stack to deal with, you know, like even like, you know, proximity sensors, for example, to say, okay, if there's, you can have a parallel system, right? That's basically saying there's something right in front of the car right now, we can slam on the brakes. We don't know what it is from the detection system, but we know enough to say that this is unsafe to try and go through. In terms of the difficulty of the problem, I think in general, you know, like people talk about self-flying cars, and that seems like an easier problem than self-driving to me, because there is so many actors that are doing things, a lot of them unexpected when you're driving on the road, and there is no, you know, regulation around where people are supposed to be. I mean, there is technically a little bit like sidewalks and crosswalks, but of course we know that's not where people are when they feel like not being there. So so it's a very big scale problem, but I don't think, like, Facebook is to me not the right analogy, in the sense that Facebook is a complicated engineering system. There isn't like the level of new scientific discovery that is required in order to make Facebook is not humongous. It's the humongous effort is engineering. Like, how do we make sure that everyone gets their notifications in time, and things like that, which are really about scaling, or, you know, maybe it's system engineering type of research. Whereas here it's more on, yeah, research on effectively a lot of machine learning types of problems, as well as hardware control systems and so on. So from that perspective, it's more similar to your NASA type challenges.
Yeah, so I guess like we do, I guess, like have a different approach asymptotically, right? And so I think that the question is essentially compared to the way a human would try to drive, or, you know, if you're a human driving, right? Like, how many of the things that you're looking at, if you were to pretend that, okay, I actually don't understand what some of these things are, how well could you drive under those constraints, right? And so it's not super clear. And it's also, what's also not clear, right, essentially is, well, actually this part is more clear. So I think it'd be hard pressed to find objects that you find in the real world which you've truly never seen before, right? Like whenever you're looking at a given scene, it's very unlikely you'll see something you've literally never seen before, or at least something very similar to it, right? So, and those kinds of priors could actually be very important for allowing humans to understand their environments, especially in corner case scenarios, right? Determining whether it's a rock or a tumbleweed or something like that, or some corner cases for judging complex pedestrian behavior in like urban driving scenes, right? So, I guess our view is that we think that it's probably going to be necessary to actually have the kind of system that can learn from very few examples and do that across a very wide set of object categories. So at least that seems like a more, if you can make that work, then we'd be more confident in that kind of system actually scaling in a worldwide scale kind of scenario. And as far as whether that's tractable, I actually do think it's tractable, because essentially the bottleneck for training AI systems today effectively is for computer vision, let's say, and the reason I keep referring to computer vision here is because I do think that's the asymptotic bottleneck to L4 autonomous driving, right? So LiDAR and radar can't actually provide enough information for you at the tail end for a lot of different corner cases, at least for those more refined types of judgments, as I mentioned, right? Instead of doing more of a kind of anomaly detection type of approach to kind of try to bound the tail end. And so, for computer vision, the bottleneck really is sort of, okay, well, the training actually is not necessarily that expensive. Like the difference in cost between training and annotation is like 100,000x, right? And I think we've seen what happens when you can train neural networks on effectively very, very large annotated data sets. Like one good example is GPT-3, right? So you're dealing with this like very large corpus of text that you could think of as unsupervised training, but it's effectively supervised, right? Because you're essentially removing words from sentences and filling them back in, and you have humans that have written quite a lot of text, which essentially gives you examples for coherent language, right? So it's effectively a supervised learning task at very large scales, and the performance you get there is quite impressive, right? So in theory, nothing, so if you take the analogy over to computer vision, so why can't we do that for computer vision, right? I mean, we can try to do that with certain types of, in painting type of techniques, but it's not nearly as good for getting a refined level of understanding for all different objects, right? But imagine if you could actually do that at very large scales, I think we'd see computer vision systems that are well beyond what we have today if we actually ran that training. And I think the cost of that is tractable. It's a question of actually setting up that cost. So setting up that training without paying the annotation cost. And so that's really kind of the motivation for the approach that we take at Helm, using our deep teaching technology approach. So really, it's just a question of nothing's actually stopping us from scaling up the compute even further. We're essentially going after the L2 and L3 markets, right, where you end up being compute bottlenecked well before those kinds of much bigger neural networks can actually come into play. So as far as whether it's, comparing to, again, I don't know if Facebook is the right analogy either. I think that, I don't know. I guess I actually do think that it's like tractable. So I think it's maybe, I don't even know if I would compare it to like landing on the moon or something like that. I think it's actually more tractable than that.
Okay. And we get a lot of questions around LiDAR, I think justifiably so, because there's a lot of investments in it. There's a lot of people who spend a lot of resources advocating for the use of LiDAR. Some people view LiDAR as kind of a backup to cameras, while others will tell you that, without the camera validating what the LiDAR sees, it's actually not useful at all, and so it's not really a backup. If anything, it's kind of in series. So what do you guys think in terms of the usage of LiDAR? Is it a crutch, as Elon Musk likes to put it, or is it something that is necessary and is going to be there as part of the self-driving stack going forward? And I guess along with that, HD maps, since there's pretty good use in localization with LiDAR. If you guys could just kind of respond to Vlad, maybe if you could go ahead on that.
Yeah, sure. I mean, so as I was saying, right, like I think that so LiDAR and radar, essentially the limitation there is on the resolution, right? As well to some extent, to a large extent also the range, as well as just semantics, right? So I don't think, so if I gave you even like perfect LiDAR and radar and asked you to go driving, like I don't think you'd want to do that. Like, it just wouldn't be safe, I think, to do that, especially at the tail end. So I do think computer vision will have to play a key role, but I think that there's some conflation. That doesn't mean to imply that LiDAR will never be present on L4 systems. I do think it'll be present there for redundancy purposes, right? But in terms of what's at the heart of like the challenge of actually making L4 scale, I think it's really computer vision. So, I mean, yeah, I don't think that just by using LiDAR, you can overpower the problem.
Inmar?
So first of all, I think you cannot drive with LiDAR only for one pretty simple reason, because you need to know the state of traffic lights. So there is like a place where, it's not an edge case, it's just something that you need. But you can get pretty far. Other than that, you can get pretty far with LiDAR. It's a very powerful technology because it doesn't, like, ultimately, what you need to know is how far are things away from you. And camera information does not provide that reliably, right? And that's really the issue here. So the question is, how fast can we get to a point where we are estimating distances reliably based on, several cameras where you can use the parallax, or a single camera where it becomes a really, really difficult problem? I think it's solvable. I think we want to get there because the LiDAR is just a very expensive piece of technology. And we'd rather just get away from having to use it. But there is also a question of safety. So from the point of view of allowing for a car that really drives itself without assuming a driver behind the wheel that will take care of things when there is a risk and control needs to be taken away, then for now, in terms of where the technology is, it's an important piece of technology. And LiDAR and radar are quite different in terms of how they're used. Radar is like definitely a nice to have. I don't think there is a